Question 10 is another vector question, another important one for you to be able to do for Physics 30, but this time we're dealing with forces. So we have two people pulling on an object, both at a 30-degree angle and both with 70 newtons of force. So this question, because they're pulling at with the same angle and the same force, 70 newtons, then this question is makes it a lot more straightforward with those things being the same, because basically we solve for one triangle, we've solved the other one. So one guy is pulling in this direction with 70 newtons of force. At a 30-degree angle, and you can use trigonometry, sine and cosine to solve for x and y. In this case, x is going to equal 60.62. And y turns out to be 35 newtons. All right, so that's for person A. For person B, because it's the same angle and the same force, they're almost identical. X is exactly the same. The only difference is that y is negative 35 because he's pulling in a different direction. So his y component is down and A is up, if you want to look at it that way. So this is for person A. For person B, x equals and y equals negative 35. All right, so now we can, what we want to do is we want to add, we want to find out the total, the resultant vector between the two people pulling, and then we're going to take into account that friction force of 100 newtons. And so we can say that our total x is 60.62 plus 60.62, which equals, does that equal 121? And your total y equals, let's write it out, 35 plus negative 35, 0. And that's what makes this question easy, because the resultant vector is just straight horizontally that way, and then the friction of force always opposes the motion. So this is 120, and this is 100. Then the net force, is that what it's asking? What is the net force on the stone is going to be A, 21 forward. Okay. On to something a little different. At the surface of the Earth, an astronaut has a gravitational mass of 80 kilograms at a location where the acceleration due to gravity is 10 meters per second squared. What is the force of gravity on the astronaut at a location 1 Earth radius above the Earth? There's the Earth, there's the astronaut, and at that point, you could calculate the gravitational force acting on the astronaut because you have enough information that Fg equals mg. However, it's probably best that you do this question just using ratios and relationships. That's always a preferable method, because then you can apply it to any situation. You can make generalizations about situations as opposed to having just specific numbers. So at this point, he's on the surface of the Earth, and this is 1 Earth radii, and then we're going to move him up here so that he is now 2 Earth radii from the center of the Earth. So actually, let's just, given this, we've written this out, let's just do it this way. I'm going to have to do this calculation at some point anyway. So his mass is 80 kilograms. acceleration due to gravity is 10. Therefore, the force of gravity acting on him when in this situation, should have done that in black, is 800 newtons. Now we move him up here. So the distance between him and the center of the earth is twice that. And we want to calculate his new force of gravity. And as I said, you're going to do that just with the relationships. You're going to say, this is the equation for the force of gravity, or gravitational field strength. And therefore, the relationship between the distance and the force of or the gravitational field strength it's an inverse relationship. Actually, sorry, I wrote down the wrong formula. Well, we can do either one. That's better. So the force of gravity equals G m1 m2 over r squared. So now the relationship is that the force of gravity is directly proportional to 1 over r squared. And now instead of having a radius of 1, we have a radius of 2, and it doesn't matter what that actual radius is. This is the radius of the Earth. And if you want, you can plug that number in and multiply by 2. But if we do relationships, it's just a lot easier. So instead of putting a 1 for the radius, you now put a 2 for the radius because it's double the radius. And that gives you 1/4. So now the force of gravity acting on the astronaut is 1/4 of what it used to be. You doubled the distance, but the gravitational field strength is 1/4 because of that inverse squared relationship. So then you can just take your 800 newtons multiply it by 1/4, and you're going to get the answer, which is 200 newtons. So you can probably see how it would be easy on that question to say, well, you double the distance, so don't you just have the gravitational field strength? Well, no, that's not true. It's because of this. It's because of the r squared. All right, number 12. Number 12, a 56 kilogram mass is traveling in a circle with a radius of 3.75. And the frequency of the revolution is 24.6 RPM, revolutions per minute. What is the centripetal force acting on the mass? This is the formula that we associate with centripetal force, mv squared over r. It's one of those formulas you should memorize because it's not on your formula sheet. So what do we have? Well, we have the mass. We have the radius. We don't have the velocity. And how do we calculate the velocity of something going in a circle? Two pi r over t. And just a reminder, that's just the derivation of this formula here. And in a circle, the distance is the circumference of the circle, and the t is the time that it takes to go around the circle once. Do we have t? No, we don't. But we do have 24.6 revolutions per minute, and we want to find out how long does it take to do one revolution. So you could just do that as a proportion if you want. You could say 24.6, say cycles per 60 seconds equals x over 1 cycle, because period is how long does it take to do one cycle. And then cross multiply and divide. And you are going to get x equals 2.44 seconds. And now you can plug that into this formula here. Oops. 2.44, and that will give you a velocity of 9.66. And now you can plug it into this formula here. Don't forget to square the velocity. Radius is this. And it's going to give you an answer of 1,394 meters per second, which is D. All right, let's get another one in here. Number 13, what is the gain in kinetic energy if a mass of 5.25 kilograms increases the speed from 5 to 9 meters per second? So we want the gain in kinetic energy. We're really talking about the change in kinetic energy, and the change is always the final minus the initial. And this is a simple kinetic energy question. In other words, EK equals 1/2 mv squared. So find out what the final is, subtract the initial, and you get the change. Okay, and you can just plug the numbers in at this point. If you want, you can factor out the half and the m, but that's totally up to you. Don't forget to square. And that's going to give you an answer of 147, so C. Onward to number 14. Number 14, we have, looks like a mechanical energy question. You have a block. And notice that the block is on a sloped hill already at the top here. So it already has some velocity. If it already has velocity, then it has kinetic energy and potential energy. Right? Unless if the block was motionless, then it would have only potential energy. And then once you push it and starts going down the hill, it gains kinetic energy and loses potential energy. So this question says the above diagram shows a block on a frictionless hill. At the instant it passes over the point at tip H1, it has a speed of 3.8 and is 4.75 meters above the base of the hill. What is the gravitational potential energy at H2 if the speed is 8.8? So this is a conservation of energy question, conservation of mechanical energy. And we're just going to figure out what the mechanical energy is at the top here. Oops, sorry, I did that backwards. I'm just going to do it over here. That way I'm close to the mic. EM, and I'll do it correctly this time, equals EP plus EK, which is MGH, that's EP, that's EK. Plug the numbers in. 1/2 times the mass, what's the mass? 9.5 times gravity. A reminder that you don't use the negative because energy is not a scalar, or is a scalar quantity, not a vector quantity. And it is 4.75 plus. And the velocity at that point is 3.8. And don't forget to square it. And that is going to give you a total mechanical energy of 503 joules. So remember that throughout the entire process, as it goes down the hill, the mechanical energy will always be 503 joules, because that's the conservation of energy. Now, when it gets to point H, 2, it has lost potential energy and gained kinetic energy. And so what we're going to have to do to find out, the question is asking for the gravitational potential energy. We're going to use the same formula. But this time we're solving for the gravitational potential energy. So it's just going to be EM, the mechanical energy, 503, minus the kinetic energy at that point. So there it is, minus 1/2 mv squared. Plug those numbers into the calculator and you're going to get the answer, which is 141 D. Okay, we'll stop there for this video.